can be translated to the integral over the closed surface if this is a volume. So you know that. And this looks like that, but this is in 6 dimensional space. It's difficult to be sure that the divergence theorem or the Stravinsky theorem is working in the higher dimension than 3. It's not very trivial. It's absolutely not trivial. But we will accept that. If you want, you needed to check the books for the higher level advanced calculus. So we will see that. Anyway, we accepted that. We say that it looks like the divergence of this. Yeah, it looks like a vector. So it looks like the vector field, and it looks like the divergence operator. Yes? So I just continue that. Plus, so this is, I don't do the calculation. I just keep it that for the last step. Still, I'm looking for a general proof for this theorem, not for microcanonical, because for microcanonical you are doing many simplifications. Like at the first step you relax the rho, and if you don't have the rho, so every life will be easier. Huh? I'm looking for the more general, also for canonical, not so difficult. It's difficult but not so difficult. You know why? Because canonical means that the rho is a function of Hamiltonian, and you are working with something like Hamiltonian here, so you can make it combine these two. So anyway, so can I write this integral as what? As the integral over the surface, huh? Over the surface. So xih dot some vector area of that, so one dimensional lower than that. So I mean dq, dq2, dq, if I write this dA omega, for example, so will be dA omega, for example, dA omega I minus 1. How I can write that? I want to show the surface just one dimension lower than the volume. Over the surface, what is the boundary? The boundary is when h is equal to E. H is equal to E. And this notation still is confusing, so I don't know. I needed to write ni here, for example. D omega I minus 1, like that. I'm just developing this time. Okay. So this term actually will be 0. So we can relax this term and set it as 0. Looks like that. You do the integration and the A is equal to A. It looks like that. Because you pass to the boundary. So the boundary was from 0 to H, and the H was bounded between 0 to E. I mean, you fix it exactly on the boundary. You are making the integral like that. Before, it was an integration in the... So it looks like that This is a one way. So you can forget about that. It will be safe. The only terms remain here is that. So you will be very careful about this integral actually. We need to develop the Leibniz rule. So partial derivative of alpha a, I alpha, b alpha a, f x and alpha dx is partial derivative of I alpha a, b alpha a, partial derivative of x alpha dx plus b prime alpha a, f b alpha 1 alpha minus r prime alpha a, f r alpha a alpha. This is a Leibniz rule. So we have all the ingredients to complete the proof. There is another way to forget about this. The last the thing is that they inserted the e at the beginning to the integral, and finally they say that okay, it's over the surface h equal to e, so that term will be 0. But I don't very much like that. So the only term which you needed to work is that no. I will use the Leibniz rule. Yes, I will use the Leibniz rule. So that will be delta over omega delta ij omega 0, I mean. That was omega 0 always. Omega 0 delta ij. Okay. Integral is 0 to EA, partial derivative of h in respect to EA. dq pair plus partial derivative of the e with respect to e h when h is e, and the second term is 0 because from a to b a is 0 always. Okay. Oh, we have one minus here, and we forget the minus. Minus comes to here and also to here, huh? And also to here. Okay. If you're not happy from that, from this proof, I can tell you that this term can be cancelled by one of these terms also. But I don't want to make it this very bold, so it's not very big issue actually. Yes. B prime alpha, f, okay, B alpha, yes. That's all. Integral 0 to e, partial derivative of h in respect to e dq df minus delta omega 0